we're going to quickly just review some of the stuff that we've learned already and then go from there. All right. So here's some of just the things that we know so far. The first is the root mean squared voltage, or the voltage RMS. And that's equal to, now I'm going to write it a little bit different than I normally do. I'm going to write that as VP over square root of 2. And VP just means the peak voltage. Some textbooks use maximum voltage. A lot of textbooks call it the peak voltage. It's the same thing though, okay? And then we can do the same thing with the current, I, RMS, and that's going to equal the peak current divided by the square root of 2. So we've defined those from previous lectures. What else? We have the, what is it called? The capacitance reactance. Capacitance reactance, XC. And that's just the resistance of the capacitor. And that's equal to 1 over, what is it? Omega C. Or we could write that as 1 over 2 pi times the frequency C. Okay, so that was the capacitive reactance. Then we have the inductive reactance, and that's equal to omega times L. That's equal to omega times L. Or we could say 2 pi frequency times L. So this and L are proportional. This and C are going to be inversely proportional, or W and C. And what is W? In this scenario, we define W as the natural frequency. W is equal to 1 over the square root of L divided by C is the natural frequency. Now, something else you want to know is the power lost from a capacitor. The power that's dissipated through a capacitor is equal to 0. You don't lose power through the capacitor. You also don't lose power through an inductor. So the power lost through an inductor is also going to equal 0. However, when we're talking about the power from a resistor, the power through a resistor lost is equal to I squared times R. That's how we typically write it. But we're going to be talking about the average power lost. And the average power lost is going to be given by this equation right here. So the average power lost will equal I RMS. I don't know why I keep using capital and lowercase. They're the same I. Times the voltage RMS. And then we're going to add this new term, which I didn't talk about yesterday. I should have put a question mark next to it. Times cosine of the phase shift, phi. And this right here is called the power factor. So cosine phi is defined as the power factor, and that is going to be equal to the resistance in a series circuit divided by the entire impedance, Z. All right, so that is the power factor. All right, let's keep going. Is there anything else? That's all I want to say about that. Let's quickly look at different types of voltages that we can get in different scenarios. So I'll put that over there on the side. My goodness, it is getting hot in here. So the first scenario is just the resistor. if we just have a resistor connected to an AC supply, we say that the voltage of the resistor is equal to I times R. Okay, that's not so bad. If we do the same thing with a capacitor, then the voltage of the capacitor is going to equal I times the capacitive reactance. And if we did the same thing with a AC current or an AC voltage connected to a inductor, like so, then the voltage of the inductor is given by I times the inductive reactance, L. So that's not so bad. But what if we start combining different things, right? What if we started to combine these? So let's erase this. The first one we could do is the RC circuit. If we're talking about the RC circuit, we have an AC voltage, and then we have a resistor here, and we also have a capacitor. That's our RC. What would our equation look like then? Well, I, the current, is going to equal the voltage divided by the impedance, not the reactance, and not the resistor anymore, but the impedance. And in this scenario, the impedance, Z, is going to equal the square root of R squared plus X of the capacitor squared. I don't know if you can see that, but there it is. And that is the RC circuit with an AC power supply. Then we can do a AC power supply, and we can connect it to a resistor and an inductor. So now we're looking at the LC circuit with a AC voltage. What would happen there? Well, the current is still going to be defined as the voltage divided by Z. And in this case, when we do Z, when we solve for Z, it's going to equal the square root of R squared plus the inductive reactance squared. That's an L. Okay, so far, so good. Nothing too bad. Everything is wonderful. Now let's talk about the RLC in series, and we're going to be doing phase shifts for these as well. So if we had an RLC circuit with an AC power supply, we would get something that looks like this. We got the resistor, the inductor. Whoa. 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 There we go. So what's happening here? You're going to have three different voltages. You're going to have one voltage from here, and that's going to be the voltage of the resistor, and that'll be equal to I times R. But then you have a voltage between these two, which is the voltage of the inductor, and that's going to equal I times the inductive reactance. And then you're going to have the voltage here, which is going to be the voltage of the capacitor, and that's going to be I times the inductive capacitance. And it would be really easy to say, well, if that's the case, then we know the current here has to be the same because it's in series. So then the equivalent resistance would be this plus this plus this. But it is not, because this and this are doing the opposite. And you got to remember that. When this thing increases, this thing will decrease. They're like doing the opposite of each other. They're 180 degrees out of phase. So what would Z equal, the impedance? Well, the impedance is given by this equation here. We can still say, where am I going to write this? And I think I could write it right here. I is still equal to the total voltage divided by the impedance. We can still make that claim, but we have to be careful in how we write our impedance. The impedance, Z, is going to equal the square root of R squared plus parentheses the inductive reactance minus the inductive capacitance, the capacitance, the inductive reactance minus the capacitive reactance squared. And all of this combined together gives me the impedance of a RLC circuit. So we're good with that. Everything is good so far, I hope. There is going to be a phase shift. There will be a phase shift. So I'm just going to keep on my analysis here. Where can I do this? I'll give you a second to write this down, and then I'll erase the bottom part. There's some other little things that you're going to need to know. I'm just going to give you what the equations are right now, and then we'll derive them by looking at the phasor diagrams. So when we're talking about phasors, we're talking about the phase shifts. So this symbol right here is called the phase angle. Now, sometimes the phase angle in some textbooks is written like this. But I know that's difficult for many of you to make a fancy, this little symbol right here. I believe that's a lowercase delta symbol. So I know that's really difficult. I mean, you guys don't have the artistic skills. I mean, I've seen you try to make this. You can't make the fancy E's, so forget about making the fancy D symbols, okay? So don't even try. If you can't do it, stay out of the kitchen if you can't handle the heat. Is that the expression? So don't try that. Just use this. It's easy for most of you. I'm sorry, but we're not all artistically refined as yours truly, but that's just how it is sometimes. So that's our phase angle. And how we solve for the phase angle is we're going to get tangent of the phase angle will equal the reactance of the inductor minus the reactance of the capacitor divided by the resistance. This is all for series circuit. And then there's going to be another term that we're going to want to know, which is going to be cosine phi. And that was the power factor, what I was just talking about. And cosine phi is going to be equal to R over Z. Okay? So that's everything so far. Now let's actually look at what a diagram looks like, what a phasor diagram looks like in an RLC circuit. All right, hope you're ready. Let's do it. So let's look at our phasor diagram. So here's my phasor setup here. And we are going to use a color. What color should we use? Let's use black for the voltage of the resistor. Oh, we should draw it out too. So we have that's AC, DC. This is AC. So here's my diagram. We got our resistor here. We got our capacitor here. We got our inductor here. Whatever. It's an RLC in series. Let me remind you, it's in series because it's going to be important. Parallel is going to be very different to this. So in series, the thing that you want to remember is that it's something in series, the current remains the same. And we call this, what do we call this? We call this a driven RLC circuit. So this is called a driven RLC circuit. Now that word driven, I know might be foreign to some of you because most of you don't drive cars. You take Valos and trains, but driven means in this context something that's pushing the current in and out, and that would be from this power supply. All right. And is there anything else? So here's R, here's C, here's L, and then this right here, this is going to be the voltage applied by the AC circuit. Now, because we have this C and L term, the voltage applied is not going to be the same as the resistor. The way you want to think about it, let's slow down and make sure we get this. There's a voltage here, there's a voltage here, there's a voltage here. So the voltage here can't be the same as the voltage here, okay? So we can't say the voltage of the resistor is going to be the same as the voltage applied. They're going to be different. They're going to be out of phase a little bit because we're including these two here. So what we're going to do is we're going to start off with the voltage of the resistor. Let's say this is the maximum voltage of the resistor. Voltage resistor. And when I say voltage resistor, I mean the peak voltage. Remember yesterday we talked about phasor diagrams? The current in a resistor is always going to be in phase. So the current is also going in this direction. The current that's going through here, this whole cycle here, is going to be in the direction of the resistor. Now, let's put a little current symbol there. So the current's going this way, okay? So that's the direction of the total current. Capacitors. Does the voltage lead or sag behind the current? Yesterday we talked about this. For a capacitor, the voltage lags the current, meaning whatever the current's doing, it does it first, and then the voltage comes afterwards. So the voltage of the capacitor is going to be 90 degrees out of phase. It's going to be 90 degrees out of phase with the direction of the current. It's lagging the current. And we're moving in a counterclockwise direction. That's the whole idea of phasor diagrams. They move in this direction like that, okay? Why? Because I think in math, we start here as the incident angle, and we always move in that cycle. So that's how we're going to be defining it this way. And so if that's the direction of the voltage of the capacitor, we know that the voltage of the inductor leads the current. That's what we had defined by yesterday. So it's going to lead the current by 90 degrees. It's going to be the voltage of the, that's going to be the voltage of the inductor. Okay, so this forms 90 degrees, and this forms 90 degrees. And what we're going to do is we're going to find the applied voltage. The applied voltage is this plus that. That will give us the applied voltage. So should we do it on another diagram? Yeah, why not? Let's do it on another one. Let's do it down here. So I'm going to combine some stuff together. Oh, and this angle right here, that's important too. How could I possibly forget? This angle right here is defined as omega t minus or plus? Minus phi. So the angle of the current is omega t minus phi, because the applied voltage is just omega t. So let's do this out. The first thing we're going to do is put the resistor here. My goodness, it is hot without the fan on, but I'm going to keep doing it because I love teaching. So here, there is the voltage of the resistor. Now what you could do is these two are on the same line, so you can sort of cancel them out. We can see that the inductor is a little bit bigger than the capacitor, so the result is going to be a vector that we can use head to tail method. What color? We're going to use pink. Let's use pink. Why not? So using head to tail method, we're going to take the sum of this result right here and put it right here. And that's going to be just a little bit like that. And it's 90 degrees. Whoop. 90 degrees. And this vector right here is the voltage of the inductor minus the voltage of the, look at that. You can start to see where we're going to get that impedance equation from. So we have the voltage of the resistor, the voltage of the inductor minus the voltage of the capacitor. They're 180 degrees out of phase. And then from that, the resultant of this vector plus this vector right here in blue is the voltage applied. Okay? And the voltage applied has an angle of omega t. hopefully that's good so far. Hopefully. What am I going to do next? I'm going to make this right triangle. This is a right triangle over here. Make my life a little bit easier, because why not? Life needs to be easy sometimes. Whoa, that is not a straight line. Come on, man. Oh, that's pretty good. Admit it, you're impressed. So this is the voltage of the resistor. Then we have, whoop, going straight up, the voltage of the inductor minus the voltage of the capacitor. And finally, what color? Blue. Come on. Yeah. And that's the applied voltage. And what do you think this angle right here is going to be? Well, you compare this and this together. This whole thing is omega t. This part, the resistor part, is just omega t minus phi. So if you do omega t minus phi, whatever, plus phi, whatever, you're going to end up with this term right here, which is just phi. That's the angle between them. All right. Hopefully we're good here. We're good here. We got our triangle here. Let's do some physics now. Oh. Man. I need to get one of those silent air ACs. I think that's what we need. So here's the diagram that I have. Let's do some fun physics here. Now this is a triangle. It's a right triangle. We can use Pythagorean theorem. And we can also say, because these are maximum, this is the resistance max. This was the voltage max over, this was the voltage max of the resistor. These were all maximum values. These are, the straight arrow sizes. We can say that the applied voltage, the peak applied voltage, so applied voltage at its peak squared is equal to V R squared at its peak plus, what is this? We'll put it in parentheses, V of the inductor at its peak minus V of the capacitor at its peak, all squared. All right. So far, so good. Now, something that a series circuit has in common is the current. The current's not going to change. The amount of current that's going through here has to be the same throughout the whole system. So what we're going to do is we're going to rewrite this equation in terms of current, where this term right here, the applied voltage, is really the total current, or the peak current, times the impedance, all squared. And that's going to equal I peak, so the current peak, times R squared, plus I peak times the inductive reactance minus IP of the capacitive reactance squared. Well, this is squared. What can you factor out? You can factor out the I. And so we're left with Z squared is equal to R squared plus XL minus XC squared. And we get our equation for the impedance. The impedance is going to equal the square root of R plus XL minus XC squared. And there you have it. That is the equation that we derived from. And we derived this using our phasor diagrams. That's why they're so important. You can derive things like that and sort of, make sense. Now, some other stuff that you might want to know just on the side right here. Well, I'm saying that this is equal to that, right? So we could say that the peak current is going to be equal to the voltage applied at the peak divided by Z. Now, that's the peak current. What if I just want the current? If I don't want the peak current, but I just want the current is in the same direction as R. So if I want the current, not the peak current, I is going to equal the component of that. It's going to be actually, what do we say? It's going to be I'm trying to get it out. It's going to be the projection of this phasor right here. So we'll still write the same thing, applied P divided by Z, but we're going to have to take the component of this, not the entire thing. And the component is going to be written as cosine omega t minus phi, because the current is in the same direction as the resistance. So that is the current equation here, where this term right here, the voltage applied at the peak divided by Z, is the peak current. So we could, one more time, clean this up a little bit and write it as I peak times cosine of omega t minus the phase shift. Woo! Okay. Now, let's do some fun thinking here. What happens when this value, XL, is equal to XC? If XL is equal to XC, and by the way, it doesn't really matter if it's XC minus XL, it's squared. So if the vector from the capacitor is much larger than the vector for the inductor, you could do capacitor above this, but it's going to be a negative value. But when you square it, it doesn't matter. Okay? What was I going to say? What if XC is equal to XL? Then the impedance is equal to R, right? So what if the resistance from the capacitor is equal to the resistance? Let's see what happens. So if we say that XC is equal to XL, if we say that XC is equal to XL, well, XC is 1 divided by omega C, and XL is equal to omega times L. And so what do we end up? Let's solve for omega here. If we solve for omega, we will get omega is equal to, wait a minute, you get the natural frequency. If XC is equal to XL, you will get the natural frequency, omega naught. And that's going to be really useful to try to get this natural frequency, because the natural, if you match this right here, this is going to equal the natural frequency. So whenever you have something that equals the natural frequency of something, you get a term called resonance. Remember when you take a little glass and you have a little bit of water on there and you turn it, you hear that. That's the resonance. That's when you spin it, the frequency of your spinning thing that's rubbing against the glass matches the natural frequency of the glass. You can do something similar with this. If you get this natural frequency, you will create a resonance. And what kind of resonance we'll see, I'll show you. So we get a resonance when we do let's look at the power versus, let's look at the power that's lost or power dissipated times frequency, the angular frequency, where this right here is going to be omega naught. So the way the power versus the frequency works is you're going to get graphs. Let's say you have a specific R value. So in your RLC circuit, you have, oh, this pen's not opening. At a specific value, now I don't even want to use this pen. Stupid pen. I'll use this one. if you had a specific R in your RLC circuit and you plotted a power versus the angular frequency, when you get to the natural frequency, you will reach its peak value. And so you'll get something that looks like this. Whoa, and then it comes right down again. So this will happen for small resistors. So small R's. Okay? For small R's, you'll get something that looks like that. Now, if you replace the resistor in your RLC circuit with a larger resistor, you will still get a peak at the natural frequency. It just won't be as high. So it'll look something like that. So that's for larger R's, large resistor values. You will get a graph that looks something like that. Anything else I want to say about this? So there's a factor called the Q factor that you learn in damped harmonic oscillators. There's a Q factor that goes with this, and the Q factor pretty much tells you how intense the power peak is going to be. So a large Q factor means that the peak is going to be higher. A smaller Q factor means that you're going to have a smaller power resonance value here. So you create this resonance when you reach the natural frequency. Now, what is the Q factor? The Q factor is given by this term right here. Ooh, Q factor. Do you need to know this? Well, not really, because you don't really need to know anything at this point. But it's good to know. It's omega naught. It's the natural frequency times the inductor divided by R, where if I was to relate this to a harmonic oscillator, like a spring on a block with a spring, R would be, I guess, like the drag coefficient, the B in like minus BV, and L would be similar to mass. So that's that. And then if this value, if the Q factor is bigger than 2 or 3, then we can approximate another equation for the Q factor. And that's going to be given by omega naught divided by delta omega, which will equal frequency divided by delta frequency, not the natural frequency. And you might ask yourself, what is delta omega naught? That is going to be given by, what color am I going to use? Using a lot of colors here. This right here is the average power, by the way. So this would be the average power max for this red. Average power max, I don't need to do that. And what we do is we go halfway to the average power max, which is right here. This would be average power max divided by 2. And the distance between here and here is delta W. Okay, so if you take half of the average power maximum and you look at the distance between the 2 points right there, that's going to be delta W that we use. And if you do this divided by that, it'll tell you how strong that Q factor is going to be. If it's very large, you're going to get a very large spike there. How do we use this? Why is this so important here? So we use this to receive radio signals. So radio signals have very specific frequencies, okay? And what you want to do is you want to match the natural frequency of your RLC circuit to the frequency that a radio somewhere at a different town is emitting. And what will happen is when the natural frequency matches the radio frequency that's coming from a different town, you will get this peak power output at this specific current, and all the other frequencies kind of die down. And so you're only going to be listening to that one specific station, and it'll match the natural frequency. So how could you change the natural frequency? Because, you know, not all radio stations are located at this wavelength. Maybe some radio wavelengths peak at this wavelength or that wavelength. How do you change omega naught? Well, omega naught is given by 1 over the square root of LC. So if you change the inductance or the capacitance, you can change where the natural frequency will be. And that's how radios work. So you know that dial, I don't even know if you guys use radios anymore. Well, a long time ago, they used to have dials, and you can dial, change the dial, and then it would go, woo, and then you would get a radio signal. What you're doing by changing the dial on the radio signal is either changing a capacitor or a inductor that's inside of there. So there's a variable capacitor or a variable inductor, and every time you turn the dial on it, what you're doing is you're changing the natural frequency of your RLC circuit, and then it'll pick up whatever signal that the radio is picking up. So this is how FM radio signals and even AM radio signals work. And what's even cooler is you can apply this to things that come out later, which don't have the radio signal, but light signals, which is TV antennas. But there's no more TV antennas anymore either. They use digital, but they used to, before you were born, what year were you guys born? Like 2008 or something? So before 2008, maybe around like 2006, if you wanted to watch TV and you didn't have a cable box or a satellite dish, you would have an antenna, and the antenna would pick up signals from different TV stations. And when you change the channel, what you're really doing effectively is changing one of these so you could pick up that signal. Everybody always gets upset. Everybody always gets upset when I say what year they're born. All right, here. Let me put it in perspective, all right? 2002 and 2000. Well, Zoe, how dare you? If we're looking on the long, this is a timeline of the world, right? This is a timeline of the world. Let's say that this is, I don't know, the dinosaurs. And this is the last ice age that we went through, somewhere right here, ice age. Okay. And this is when America was founded. And this is when you were born. And this is 2008. It's negligible. It's negligible. 2002. 2008, same thing. We're physics people, so we use approximation symbols here. Okay? So 2002, 2008, approximately the same thing. You know when it won't matter is when you're old. When you're like 70-something years old. All right. I'll go off the tangent. This heat, without turning on the fan, is making me crazy, man. It's making me crazy. How much time? All right. Let's... I don't know if it's picking up the sweat that I'm getting here, but all right. Let's see. Let's do the driving RLC circuit and call it a day. Because I got to figure out what we're doing tomorrow. I don't have a lesson plan ready for tomorrow. We'll have to figure something out there. So here's a RLC circuit in parallel with a alternating current. So we'll have the R, the C, the L. Okay, so in a parallel circuit, it's the voltage that's the same. Remember, the voltage here, voltage here, voltage here. When they're in parallel, they're the same. In the series circuit, we talked about the current being the same. So in a parallel circuit, it's going to be the voltage that's going to be the same. And so what we're going to do is we're going to draw our phasor diagram. We will draw our phasor diagram. We will start off with the current, the maximum current. So this will be I of the resistor. And in this case, the voltage here is going to be the same thing here. So the voltage applied will be the same as the direction of the current of the resistor. And what about the current? What about the current of the capacitor? Now, when we're talking about parallel circuits, they're going to do the opposite of what the series circuit do, because the current leads the voltage. If this is the voltage right here, for a capacitor, the current leads the voltage. Or I guess you could say the voltage lags the current. So for a capacitor, we would be 90, that's 90 degrees, I think. Voltage current of the capacitor is in that direction, and the current sags behind in an inductor. So that would be 90 degrees out of phase in the opposite direction, like so. I, L. Okay. And so we can do our same diagram. We can like subtract these two. We'll get a right triangle. So it's going to be this minus that. And we will get, I'm going to just draw out the triangle. So putting these together in here, we're going to get something else like this. So that's IR. Going up, we're going to have IC. I'm just going to write it as IL minus IC. And I know that's wrong. That should be if this is bigger than this one, and we'd be pointing down. But it's going to give you the same value either way, so it doesn't matter if you do IL minus IC or IC minus IL. I think just because of convention, we always just write IL minus IC. And then we get this term right here. And this term is going to be the total current I. And it's going to have an angle that's formed, which is phi. Okay. So when we combine those, that's what we get. We got our 90-degree triangle here. So let's put it all together here. What color? What color? Let's use blue. Why not? The total current, I, is going to equal the square root, because this is a right triangle here, the current in the resistor squared plus the current in the inductor minus the current in the capacitor squared. And this is why I said it's important to know the difference between parallel and series, because it's not the current, it's the voltage in a parallel circuit that's the same. So I'm going to rewrite this as it's going to be the square root of the peak voltage divided by R, and all of this is squared. So that's I of the resistor. And then over here we have the peak voltage divided by XL and minus the peak voltage over XC squared, like so. And then the peak voltage here will come out. Over here, the total current is equal to the peak, this thing divided by Z. So the total current is the peak voltage divided by the, what is this called? Impedance. So from here, you can factor out the peak voltage and cross it out. And what we'll get is an equation for the impedance. And I'm going to write it like this. 1 over Z squared is equal to 1 over R squared plus 1 minus XL minus 1 over XC squared. And that is the formula for the impedance of a parallel circuit right here. All right. So that's how we do that. And we're, again, using phasor diagrams. The one last thing I want to mention before we call it quits is I want to go back to the series circuit really quickly. So here's our series circuit right here. And I want to show you a different way of doing this. So if you've used complex numbers before and you've looked at the complex plane or the complex diagram, whatever, what are complex graphs, where you have real numbers going one way, complex numbers going the other way, we can sort of do the same thing with the driven RLC circuit. So we could say that this is a complex plane where on this side you have real numbers, and then over here you're going to get the imaginary. So the real numbers is where you put anything with resistors in them. So let's say we had 2 resistors here. We would put a voltage of resistor here and another voltage of resistor here. We would get the voltage of the resistor going in this direction. Oops. And then going up this way would be the voltage of the inductor. Going down this way would be the voltage of the capacitor. And then you know from complex planes, you add up all the real stuff and then you add up all the imaginary parts. So here we would have the voltage of the resistor squared will minus plus the voltage of the capacitor minus the voltage of the inductor minus the voltage of the capacitor all squared. And that will be what the final value would be. That would be this right there. So the resultant of this, and this together in a complex plane will give us this answer right here. And from here, you can find Z. So this is just another way of solving for Z using complex planes instead of phasor diagrams. But it works the same because you can see that these are just 90 degrees and they're all offsets. It's just one thing physicists like to do. We like to try different types of math to get the same result. Okay, so that is it.